Hey guys, it's Chili here. Bet you never thought you're gonna see this again. Yeah, we're back. We're back with some chili pork unit action here. Now it's been quite a while, so probably a lot of you who've been following this series might not really know exactly where we're at. But, and I did this myself actually, you go back to video 7, I believe it is, the beginning of video 7. It was also before a long hiatus, and in that video you get a good overview of what's going on in the CPU. So if you're new to this, or if you're you haven't been watching videos recently, which is probably most of you, I recommend you go back to video 7. Check that out. You get a good review of everything that went into building this circuit, and generally what all the parts are and how they work. But we're going to be continuing on. In the last video, I believe I created a program. I actually wrote a program in Chili Pork Unit Assembler, and then I hand assembled it into machine instructions. And that was basically just to test out this part. This is the branching instruction section. Yeah, here's the Google Sheets where I put all the stuff in, all the information. The notes, the design documents, if you will. And here is where I had that test program, just multiplies two 8-bit numbers to give you a 16-bit result. And here is the assembly, or the machine code of that, the disassembler, whatever you want to call it. I don't know, doesn't matter. So you can get this. There's going to be a link to this in the description. Also, a link to the GitHub repository. I made a GitHub repository for the circuit, so you'll be able to find that in the description. But what are we going to be doing today? That's the question. And the answer comes if we go back and we look at this here. Because we don't want to have to manually assemble our programs. We want to have a program that does that for us automatically, called an assembler. And I made that a long time ago, like years ago. I made it. It's called ASS, and it's also on GitHub. And yeah, this takes source files and it assembles them to Chili Pork Unit Assembler. It assembles them into a file that can be read into Logisim. So if we look in the folder here, we should bring this up over here. So this is our source file, mul.txt or mul.asm maybe. Yeah, that's probably it. mul.asm. So if I look in here, yeah, that's just the program that I showed you in the Google Sheets. And if I run our program here, this one, with the command line argument, the name of the source file, I'm gonna run that, and it's gonna say, yeah, process source file, resolve dependencies, and use 38 bytes out of the 255 that we have. And then if we look into this folder here, we got mul.asm.txt, and there it is. There's the file that can be read into Logisim. So let's try that out. Let's try running the program. So we're going to go into our memory here, and we're going to load image. Go into ASS mul.asm.txt. We load that, then we want to edit the contents, because these defined bytes here, they start off with just garbage in them. So we gotta basically set them up with the values that we want to multiply. So let's do an easy one. Let's do 3 times 2. And we're gonna set, this is the output values, we want to set them initially to 0. So that is all done. Let's just make sure everything's reset in the circuit. And yeah, let's go. So we'll go simulate. Ticks enabled. What's our tick frequency? 16 hertz. That seems okay. Ticks enabled. Go. All right, and it's running and it's multiplying. Hopefully, it's oh, it's done. Okay, so yeah, we see here it's reached that infinite loop at the end when it's finished. So we can disable the ticks, and we can look at the memory, and the output is 6, right? 3 times 2, 6. And the high byte is obviously 0. So there you go. Done and done. We've done it. we have something that apparently can assemble our assembly source files and into a file format that can be read into our CPU. And that's a beautiful thing. It's going to save us a lot of time as we develop new features and we want to test them. We want to write little test programs and little toy programs. But, so I made this thing. How does it work? What's the architecture of the chili pork unit assembler, otherwise known as ASS? Well, let's just spend this video and look over what I built. There's a little bit of code archaeology here because, I made this like 3 years ago and I'm looking at it now. So let's just start with like a top-down approach to how this works. So, we're parsing our command line arguments, and if there's less than 2, that means that there was no input file, right? So if there are 2 arguments, then the second one is going to be the first thing on the command line, right? Because the first argument 0, is always just the whole, I think that's the whole line, and then after that you get the parsed tokens after the name of the executable or something like that. Maybe the first one's the name of the executable, I don't remember. It doesn't matter. All that matters is that argv1 is going to be something that was on the command line. Now I have a thing in here. I have some automated tests, very simple thing. So if you put the option run tests, it will just call the function run tests and then exit. But if you don't have that option, then what it's going to do is it is going to use argv as the name of the source file. It's going to create an instance of assembler with that string, and that is how you load your assembly file. So you create the instance of assembler, and then you call assemble on that with the name of the output file, which is just derived from the input file name. And then you're done. Just 2 things: create an assembler, call assemble. Super simple, right? Yeah, of course. So let's step through and see what is all involved here. So we're going to run this. And argv, obviously not less than 2. Obviously not run tests. So we're going to try to create assembler. Step into that. And what is it going to do? Register. Well, first it's going to initialize all this stuff. Let me just bring this down a little bit. This is too much real estate for what we're dealing with here. So we're going to initialize some, member variables here. Register operations. I'll get into this, talk a little bit about this a little later, but what this does is this is actually a function that will register all of the mnemonics, the instruction mnemonics, and also all of the directives. So you got this one function that registers them all into the container that is used for assembly. So we're just registering these, and we'll get into what that entails later on. But for right now, we're just looking at the basic flow of assembly. So we open the file, set some exceptions, try to open it here, and then we process source stream. So what is that? Let's step into that. So RAM. RAM is just a vector of unsigned cars, right? There's 255 bytes for the RAM of our CPU, and they're optional. So each one has a flag to say whether it's actually been set or not, which is probably useful for some reason, but I don't remember what it is right now, That's how it works when you're doing code archaeology. So we're going to resize RAM to the RAM size, which is 255. We're going to, again, I don't know, we probably don't need to set exceptions a second time here, but we do anyways on this iStream. We want to make sure we get exceptions when bad things happen. And then we are going to get a line, and we're going to place that back into a vector of source lines, and that's just going to be a pair of string and integer. So we have a pair of the source file line and the line number. We're just parsing this text file into a vector of source code lines. So we do that lots of times, and if anything bad happens, we check to see if it's not end of file. So if there's an exception, but we're at the end of file, that's fine. That exception is okay. We just continue. But if there's something else bad happened when we're trying to load the file, we rethrow the exception that'll propagate up, give a user a nice error. So we're done, or at least I thought we were done. Looks like we're back in here. What line are we on? Line number 18. So I guess we're pretty close, aren't we? There's a move instruction. Add, move, jump, end. Okay, so there's our end loop, empty line. There's our 4 bytes. We should be done now. Yeah, so it tries to get a line. We're at the end of line, throws an exception. Then we check to see if we're at the end of the line. We are. That means that that was a fine exception to have. It means we're done. And we're done. And there you go. So that is the constructor for assembler. It just opens the file, reads all the lines into a vector. And that's it. So the magic obviously happens in the assemble function. I'm going to step into that bad boy. And so we got a flag here saying whether we have an error. This will be useful later on. And we're just going to loop over all the source lines and process them one by one. And if we ever get an exception, we're going to set the error flag to true. We're going to print that exception out, but we're going to keep processing our lines. So if we hit a line and it's badly formed, there's a syntax error, it's not just going to throw an exception and halt the program. It's going to throw an exception, print an error, and then keep going, because you don't want to halt the program on the first error. You see, that'll make for a very annoying development flow, cycle, whatever you want to call it, iteration. So process line, and that just takes in the string for the line and the line number. So we'll step into that. All right, so the first thing we're going to do is we're going to strip comments from the line. And what you need to know, okay, we got a bunch of source files here. A few of them are just utilities. They just contain a bunch of string utilities, pretty much useful for parsing our assembly code. And one of those utilities is strip comments. So let me see if I can find it in here. I think it's probably going to be in parsing. Yeah, strip comment. And I'm just using some basic std algorithm stuff to parse strings. So all this one does is it finds the first semicolon, and it basically just strips all the text off after that semicolon, including the semicolon. Extract token white. This one is very useful. All it does is you give it a string. It extracts the first white space delineated token, delineated. So first it trims all the white space on the left-hand side. Checks to see if there's anything left. If so, it finds the first piece of white space after that, and it uses that to extract the token. If there isn't any white space, that means that there's only one, the whole thing is just a token, and you just std move out that string. But yeah, it returns an optional, so it's possible for it to not have any token, in which case it'll just return an empty optional. But yeah, that's the idea, and we've got lots of different utilities like that. They're all in here. They're not super interesting. Mostly you can tell what they do just from the name of the function. So here we strip comments. That's the first step in processing a line of source code. Then we're going to extract the first token in that line. And if we didn't get any token, that means that line was an empty line, or maybe it just had a comment, nothing else. So we just return. We're done with this line that didn't do anything. But that's not what we have here, right? Because it says .org. So, I mean, our first line is obviously a directive. It's this line here, the directive that tells you where to start assembling at. So the next thing we check for is we check, okay, is this token a label? Does it end with a colon? And it's not. So it doesn't. But if it were, this would return true. It's not. All right. So is it a name? And in my code, a name is it's a string identifier. A name could be a variable name, or it could be a mnemonic, or other things maybe. I think a register is also technically a name. So it just says, is it a namey thing? And it's not, because it starts with a dot, so it's a directive. So I think this will be false. Yeah. So we check, is it a directive? And that's going to be true, right? Cool. So let's strip off the dot. And then let's check to see if the directives container contains a directive with that name. So this is the thing you got to understand about the AS. The AS works basically with maps. So we got a map of instructions, and that will map strings to instruction objects. And we have a map of directives that maps a string to a directive. And when we assemble lines, we're constantly going to be looking up into those maps, seeing if something matches an object in there. And if it does, it then delegates the handling of the assembly of that instruction or directive to the object. So we check to see if there's a matching directive in the container, or technically we check to see if there's no matching directive. If there isn't a match, then we're going to throw an exception. We're going to say, okay, the thing you had, you were trying to use a directive, but there is no directive that matches that. So give the user some information telling them what line and what went wrong. This is very important when you're writing an assembler or a compiler. The diagnostics are the lifeblood of this tool, because if the diagnostics are crap, it's going to be a crappy experience to use the tool. So this kind of code makes up a large portion of our code base. Just testing for different error conditions, determining exactly what condition we have, and then outputting a message, a diagnostic, that will give the user a good clue on how to fix the problem. But the directive did exist, so this was false. So that means that we're going to look up into the container and get a directive object, and we're going to call process on that. And the process takes a reference to the assembler itself, takes the value of t, which is the name of the directive. So the directive takes its own name for whatever reason. It's probably useful for throwing exceptions. Takes the remaining line of source code, takes the line number. So we call this. This is going to be a polymorphic function. Step into. And now we are in the origin directive, which inherits from directive and has one virtual function, process. And this handles what happens when you process an org directive. And again, we're just going to basically go through and look for bad situations and throw exceptions for them. So first, P, extract token. So we want to extract the token that's after the directive name, which is going to be the address. Why did I call it P? I can't think of why. Honestly, it's a terrible name, but it doesn't matter too much. It matters a little bit. So we try to extract a token, P. P is going to be, OXOO, right? So first off, if there was no token, that's a problem. What else? Check for garbage after directive. So if there is stuff that has happened, there's stuff typed in after that token, that's also a problem. So we try to extract, and if we get anything, let's throw an exception. But we didn't get anything. This is a very well-formed line of code. So next thing. We try to get the type of the literal, because the literals can have different types. You can have hexadecimal literal, you can have a binary literal, you can have just a decimal literal, right? So let's get the literal type, and that'll give us an enumeration type. And so first thing we're going to check for is, what if the enumeration type is not literal at all? We call int literal type. It tells us, yo, dude, this thing is not a literal. In that case, we got a problem, and we throw an exception. But if it's not a literal, which means if it is some kind of literal type, then we are going to try to set the current address of assembly to that address. So we're going to parse the literal, get out a value, an integer value, and set the address to that value. And this is going to set the address to 0, which, I mean, it probably should have already been at anyways, but doesn't matter. So there you go. There's the processing of one directive. And the thing you got to take away from here is that the logic for each instruction or each directive is within that own instruction or directive object. So you can extend the assembler by just adding new directive types or new instruction types to the assembler containers, and you've just added new instructions. So it's very easy to extend. The basic way you go about it is, let me see here. So there's directive.h here, and that just gives you the base type. Virtual destructor, and 2 overrides for process. 1 takes, let me see here. They both take a reference to the assembler itself. They both take the name of the directive. 1 takes the rest of the line, the rest of the source code line and the line number. The other takes a label, the rest of the source code line and the line. So if there's a directive that starts with a label, like for example, let me see here, this one. So this directive starts with a label, right? Out high, define byte, and just make it undefined for now. So these boys here, they'll use the second version here, but the rest of them are going to use the first version. So yeah, you just get it's a very simple interface class. Directive defines basically just process, right? And then any directives that you make, they just have to implement process, and you're off to the races. And it's the same idea for instruction. You have a base instruction class. It has a virtual destructor and a process. Looks like process for the other boy. This is also, you can give alias instructions, so you can make an alias of an existing instruction, just give it a different mnemonic. But yeah, so that's how it works. And then in these impl files, directive impl, you create your directive type, for example, you inherit from directive, and you implement process. That's it. That's all there is to it. And then in assembler.cpp, we have this one function, register operations, and we just register. So we register, for example, a directive. The template is the type of the directive. And then here we give the name, the mnemonic. And that's it. That's how you add instructions to the assembler. So let's, directives. But yeah, let's show the next statement. Where are we? We're right here. So we've parsed the interliteral, and that should be this line of source code finished. So where are we at? Process line, done. And so we loop, we get the next source line, which is, what does it contain? LP, add loop. So this one will process a whatchamacallit, a label. So let's look at what happens when you process a label. So this one is actually going to do something different than looking into a container. Labels are just handled directly, right? So we strip any comments. We extract a token. That token is add loop with a colon at the end. So we ask, is that a label? And the answer is yes. So we remove the last character in the string by calling popback. So now we just have the name of the label. We check to see if this symbol already exists. You can't redefine a label or anything. So we look into our symbols, which includes labels and define byte, labels, things that basically mark out addresses that are defined by the programmer. We see, does this already exist? If so, we're going to throw an exception, but it doesn't already exist. So we're going to check to see if there's any garbage after the label on the line. We're going to try to extract another token, and that will fail because we only have the label on the line, which is correct. And so we call add label, and we give it the name and the current address of assembly and the line number in the source code at which that label was defined, because that might be useful information, especially for outputting diagnostics. So we go into add label, and that just validates address, makes sure that the address that we're on is a good address. And that's just get address. So we get the address, and then we step in again, and we go symbols, emplace. Symbols is gonna be a map? I feel like it's a map from string to make label. What does this return? I don't know. Symbols in place. What is a symbol? I mean, it's going to be a map. Symbols. Map from string to symbol. Okay. And a symbol is probably just going to be some simple thing that records, you know, the address of where the symbol is at. So, I mean, we could look at symbol.h and we can see, yeah, so there's a type of symbol. What are symbol types? Can be a label, thing with the colon, or a variable, thing that was defined using the DB directive, defined byte. So type, the address, the source code line, and it also remembers its own name. I mean, it's a very basic object there. So create one of those bad boys, make a label symbol, and place that into the map with the name of the symbol. And that'll be used later on when we refer to that symbol. There you go. So label, again, very simple processing there. Nothing too crazy or unexpected. What's the next line? We finally got an instruction. We do have an instruction. Move from the address of in Y into register A. That's our instruction. So let's see what happens when we process one of that bad boy. Strip comments. We extract the token. It is not empty. It is not a label. It is a name. It's the name of an instruction. So it's a mnemonic. All right. We can't start with an existing symbol. So if this name is a symbol that has already existed, like if, say, it was, what was the symbol that we just did? Yeah, so if this was add loop, that would be a syntax error. Doesn't make any sense. So we check to see if it's an existing symbol. It's not. So we check to see if it exists in the instruction container. It does exist in there. So we're going to look it up and call process, step in. And that takes us to move instruction because, yeah, it's a move instruction. So we're going to process it as a move instruction. So again, we extract the next token. That is going to be the destination. If there's no destination, that's a problem. We check to see if it's indirect. So there's a function here, try strip indirect. That's the square braces. So if we're moving into the address or into the memory pointed to by the address in A, it's going to have square braces around there. So we try to strip those braces and see if it succeeded. It did not, so it's not indirect. It's direct into that register. We're going to try to consume a comma because this should be destination, comma, source. If we don't have a comma, that's a problem. Move instruction needs a destination and a source. We're going to try to extract a second token. That's the source, S. Make sure that exists. See if there's any garbage. There's no garbage, so we're looking good. Looks like we got a good instruction here. See if the source is indirect, if it has square braces around the source. It is not indirect. But if it were indirect, and if the source were indirect, you can't move indirect into indirect in our current instruction set, so that would be an error. So, what have we got here? So if neither the source nor the destination are indirect, if we're both direct, then we want to call direct move. What is that anyways? Because I don't really know. What is direct move? All right, so apparently we have a standard instruction template. So this instruction embeds another instruction. And that instruction is just direct move. And because we're moving directly, it's going to step into this one. So direct move is a standard instruction templated with the opcode domain 0000000. What the heck does that mean? Well, I mean, if we go back to our opcodes here, you notice that for our instructions, the first 6 bits determine what instruction or what instruction class we're using here. So, for example, for a move from register to register or from immediate into register, the opcode is 6 zeros, and then the last 2 bits determine the destination and the source. Now, immediate or indirect moves, they have different opcode domains. So this one has 5 zeros and a 1. This one has a 1 in, the second place here in those 6. And then add and subtraction and jump. These all have different opcode domains here. So the first 6 bits basically determine the opcode domain. And so what I have is, instead of inheriting from instruction for every single different instruction, I create a template and I can just pass in the opcode domain, and then that it'll just output an instruction with that domain plus handling for the 2 source and destination bits. So a direct move is a standard instruction, so we can handle it with the standard instruction template. The opcode domain is just going to be all zeros for the top 6 bits. And when we process the parameters, we process with the mnemonic, the destination, the source. So we already have those all parsed up. What we're going to do is we're going to check to see the literal type of the source. We're going to check to see basically if the source is an address, if it starts with an ampersand. We're going to strip the ampersand, and we're going to get a Boolean flag telling us that the source was an address. So then we check here, int type, not literal. So if the int type is a literal, we would do this stuff, but it's not. Is it an address? It is. So when you want to load an immediate, the parameter bits are 0, 0, or just 0. So that's going to be 0 for the parameter bits for the source, but the destination, if the destination is B, then the parameter bits are going to be 1, 1. If the destination is A, the parameter bits are going to be 0, 0. So that's how you determine the destination and the source parameter bits. And then you just emit an opcode. And here is where the actual assembly happens. Here's where the magic happens. So we take the opcode domain, which is the top 6 bits, and we mash it together with the parameter bits, which determines the source and the destination, and we emit that into the memory. So let's look at our RAM here, as.ram, and right now we see it's all empty optionals, null opt. And we are going to emit an opcode into there. And there you go. And the opcode is 0, 0. That's the opcode for moving an immediate value into register, I believe it's A? Yeah. Immediate into A is just 0, 0. Now the immediate value that we're going to move into here is a tricky one, because it's the address of in Y, but we haven't encountered in Y yet. So what we do is we add a variable reference. This is like a promise that later on we are going to be filling this address with the actual, are we going to fill this memory location with the address of in Y once we know it. So we keep track of these references in the first pass, and then in a second pass we resolve them all. So let's step into it. Add variable reference. So first, okay, so yeah, we're going to get the address, the current address that we're at, which is 1. And then, yeah, return to address 1. Then we step into this. And so we've got a map, symbol references. I think it's a map. Let me just double check here because it might not be. Symbol references, it's a multi-map, mapping from string to symbol. So we use the in Y name here, and we use the same type for symbols that we do for symbol references. We're just going to place that into here. And then later on, we're going to resolve the symbols in the symbol reference container to the actual symbols that we define using things like labels and define byte directives. So this is just basically a promise that there is a symbol, there is a line of, or a piece, a memory location that is referencing some symbol. So at a certain address, there's a reference to a symbol, and we need to resolve that later on. So it's going to do that. And then because that corresponds to an actual memory location, we're just going to emit a placeholder, which is EE. And that will be filled later on when we resolve the reference. And that's it. We're done there. And I mean, basically, this is how assembly proceeds. We just process lines one by one. We check to see if it's a label or if it is, an instruction or directive. And if it's an instruction or directive, we pass it off to that object to handle. And it's just going to go down the line. So the next one is an indirect move, right? moving from the memory location pointed to by A into A itself. So here we're going to load in Y, basically, is what we're doing here. So step into that. And we look, we strip. Is it a label? No. Is it a name? Yes. Is it a symbol? No. Is it an instruction? Yes. Step into that. What are we going to do? Strip. Get the destination. Check if it's indirect. Is it indirect? Destination. No. Destination is not indirect. The source is indirect. Strip the comma. Check, get the source. Make sure there's no garbage afterwards. Check if source is indirect. It is. If source and destination are both indirect, that's a problem. If neither is indirect, that's a simple direct move instruction. So we're going to delegate to that. Otherwise, if the destination is indirect, we're going to do processing for an indirect destination. It's not. If the source is indirect, which it is, then the parameter bits are 0. If the destination value is equal to B, we're going to mash this bit pattern into there for the destination. It's not. If the source is B, meaning we're going to be using the address in B to perform the load, but we're not. So the parameter bits are, the low 2 bits are going to be 0, 0. And then we're going to use the opcode domain for an indirect source, which, if you want to refer here, indirect source should be 0000001. Let's look at opcode domain for that. Indirect source 0000001. Matches. Does exactly what you would expect. So we emit that instruction, and if we look into here, there we go. That instruction has been emitted. And I mean, this process is just going to continue. So if I just step over this top end here, you can see, oh, this is out of scope because this, okay. Yeah, I should have been looking at this RAM here because we're in a different scope. But yeah, if I step over the stuff here, you will see the RAM filling up with instructions. I stepped in. God damn it, I'm fat fingering this all to hell. I don't know how many are left actually, but let's try and not fat finger it. Yeah. Fills up the memory. If I would do it a little slower, it would look better. Step over. Yeah, filled up the memory. Yeah, so there you go. It's just running through these lines and filling the memory with our instructions. At some point, it is going to reach an org. Probably soon. What's the next line here? That's a move. Not what we want. Add loop. End. That's a label, so it's not going to output anything. Then we have a jump to the end. That's the infinite loop jump. Next, we're going to have an org. No, next we're on an empty line. Then an org. And that is going to set the assembler location to FO. So if we look at this and we look at address and I step over this, it's been set to FO. And then if we look in our memory here at FO and we start to process lines, it is going to start to fill them with EE, which is the placeholder for defined byte when you just want to, define the byte and address, you want to give it a value. So there we got EE there. And if we step over again, we get another EE, we get another EE, we get another EE, and we're done. We should be done. Yes. So now we check to see if there were any errors during the first phase of assembly. If there were, we're going to stop right now. We're not going to try to resolve references. It doesn't matter. We're just going to give the user their list of syntax errors, tell them to get their shit together before we finally assemble this thing. So if there are any errors, we throw exception. If not, we say the source code was successfully processed. Now we resolve dependencies. So now we see whether all those things that we were referencing, whether they actually match up to existing labels or defined bytes. So we step into resolve dependencies, and we're going to loop through symbols. Looping through all the symbols. I can't figure out why I have these two iterators here. Hopefully it'll make sense later on. All right, so I'm making 2 iterators. They both point to the beginning of the symbols. Next iterator points to the one afterwards. So, I mean, I could have just done symbols.cbegin ++ or something. I don't know. Hey, but I want to do it every iteration. I want next iterator to be pointing to next IT. I don't know. I feel like I could just erase this line. It would do nothing, but it doesn't matter. This is code archaeology here. We're digging into the past. It's not important. What's important is that we're looping through all of the existing symbols. So we set a flag unreferenced. That's going to tell us whether there were any unreferenced symbols. IRP. Probably give these things, better names, but it doesn't matter. What this is we're finding in the multi-map of symbol references, we're finding all the symbol references that match the name of the current symbol we're processing. So we do equal range. That will give us a range of all the ones that match. And then we loop over that range. We want to make sure that the types match. So, and this is an optional thing that I've added in, but basically a jump instruction reference should match a label, and a move instruction reference should match a defined byte or a variable. So we're making sure that those match up. If they don't match up, we're going to throw an exception. And then what we're going to do is we're going to fill the RAM at the address in the reference with the address that's stored in the symbol. And then we're going to erase that from the list, from the multi-map of references. We're also going to say that, okay, so this symbol was referenced at least once in the loop, so it is not an unreferenced symbol. We get rid of the reference to that, and then we go back and we look at the next one. So we loop through all the references to the symbol, we resolve them all. If a symbol was referenced at least once, we can remove it from the container after resolution, and we're done. And yeah, we're going to do that for all the symbols in the container. We're going to resolve those references. We're going to keep track of ones that were unreferenced. All right, I skipped over it, but after you're done that, we're going to check to see if there are any symbols remaining that haven't been erased. If that's the case, that means that there was unresolved references. You specified a label or a defined byte, but you never used it anywhere, and we're going to output a warning for that. We're not going to halt. We're not going to throw an exception. We're not going to halt execution. We're just going to output a warning saying, hey, dude, maybe you're doing something here you might not have wanted to do because it's not doing anything. So just consider it, bro. And then we loop through all the remaining symbol references. And this is an important one. This one is an error because if there are symbol references that are remaining that have not been resolved, that means that there are placeholder bytes that have garbage values in them that have not been filled with real, addresses. So in that case, we're going to have to throw an exception. We're going to have to halt assembly because we have a malformed program if we just emitted the bytes as they were. So we loop through all the symbol references, see if there are any that remain, output diagnostics for them, and then if there are any that have remained, throw an exception. Otherwise, we're done. We have resolved all the dependencies. The final step is just to take those RAM bytes that exist in our vector and to output them to a file that can be read by Logisim. So create the output file stream. We output the header thing that Logisim requires. We loop through all the bytes in the RAM, and we output those bytes. Every line contains 8 bytes. So if we reach 8, we got to insert a new line there and reset the count. But yeah, when you're done that, run to cursor here. We're done that. We're going to output some messages telling the user, how many bytes we used, so forth. And then we're done. We're done assembling. We're done the program. We'll just wait for the user to press a key on their keyboard and finished. That's it. That's the whole flow of how assembly works. But yeah, that's mostly, I guess, what I wanted to show here. Let me see. Trim. This is just very basic utilities for string trimming. Parsing. more specialized utilities for parsing stuff for our assembly language syntax. So many tests to see if a token is a thing, is an address, is a label, is a directive, and parsing that will strip things, parsing that will consume tokens, etc., etc. In the process of stepping to the code, we've stepped through everything in assembler.h pretty much. I mean, there are these registers that are just templates that put things into the containers, into the instruction container, into the directive container. Most of the interesting stuff from the point of view of, as we grow our CPU, we're going to be adding things to the assembler. The interesting part comes in here. In instruction.h, we have our base instruction, then in instruction impl, we have our implementations, and those are often based on templates. So you have standard instructions, which have a very simple encoding. So standard instruction includes the direct move. It includes things like subtract and add, and in the future, things like logical or, logical and. If we give multiply and divide, those will all be standard instructions. The encoding will be 6 bits for the domain, 2 bits for the source destination. And then you have, there are going to be many special cases that require special handling logic. Like, for example, indirect move, that has its own logic. And jumping has its own logic. So if we look into here, we see immediate jump template. So this is jumping to an immediate address, and it has its own logic here. There are parameter bits. These parameter bits basically determine the logic of the jump, how it tests the carry and the overflow bit and the 0 bit or whatever. Those are all encoded in this binary bit pattern. The opcode domain itself is fixed. So you have the parameter bits plus the opcode domain give the full picture of the domain. Encoding is obviously different for a jump than it would be for a standard instruction, because a jump doesn't have a source and a destination, right? It has n, x, y. So those are those parameter bits. So yeah, obviously you're going to need a different handling, but it can also be templated to reduce the repetition of code, because, there are many different jump instructions. So we have, non-conditional jump, jump if equal, jump if above, jump if below, jump if not equal, jump if not above, jump if not below, and they all have their different parameter bits. And then some jump instructions, like jump if 0, is the same as jump if equal. So we just register an alias, which is just an alias instruction that will delegate to the actual JE instruction when it finds this in the source code. But yeah, the basic way I see things going forward is when we have new types of instructions that have, different variations, we'll create a template for that instruction that inherits from the base class. And the template will be parameterizable to a certain degree. And then in assembler.cpp, we'll instantiate all the different variations of that instruction class using the template parameter bits. Or perhaps other kinds of parameters, who knows? It's free, right? We have it's very easy to extend this in terms of adding mnemonics and adding directives. But yeah, that's it. That is the AS in a nutshell. And it works great. You give it an input, it gets you an output. Does it contain bugs? It probably does. I'm not going to lie to you. I didn't do extensive testing on this. So, we'll likely run into some bugs as we write different programs. But for the most part, it's pretty dang sweet. There was one thing that I might want to add as an additional feature is I might want to have the option to output the machine with the source code side by side. That would be very useful for debugging the assembler itself, because right now the output is just this, and it's hard to look at this and then say, does this match this? It's kind of tricky. But if I could make it output, basically an assembly file that looks like this, where you have the source code line, and then beside that you have the address and the opcodes or the machine bytes, that would be very useful for debugging the assembler itself. And that's something I might add in the future. Probably won't make like a whole video out of it, just kind of tell you, yeah, I added this and show you how it works. But yeah, so now we have the assembler. Now we can have a quick way of writing new programs to test out the new features that we add to the CPU. So the next step is to add something to the CPU. Because that's the fun part, right? That's the whole point of this series. And I think what I want to add to the CPU to start off with, like this is super annoying. Every time I want to load from a memory address into a register, I've got to load the address into the register, and then I've got to indirectly load from the memory into the same register. And storing into a memory location is even worse because you have to use both registers to do that. You have one register that is going to be the data that you want to store, B, and then you have to use A as the address to store into for the indirect storage. So you have to have both registers free to store a single value, and that can be pretty limiting, can make your life harder for programming, can make your programs longer, can make them more difficult to read. So what I want to do is I'm basically going to have it syntax like this. If I wanted to move from in A or in Y into register A, I just like to have this syntax here. So move indirect from the address of variable in Y into register A. And that'll make my source code shorter. It'll make my byte code a little bit shorter, and it will make it easier for me to juggle data in my registers. So yeah, that's what's up next on the docket. We're going to add a new move instruction, probably down here, or I don't know where, but it's going to be a different type of move instruction that will take an immediate address and load the value at that address into a register, or vice versa. But until then, thanks for watching. I hope you enjoyed this video. If you did, please click the like button, helps a lot. And I will see you soon with some more chili pork unit.